All right, folks, for those of you that have been looking to upload notes before the class starts, I just put them up and modified things about 5 minutes before I came up here. So that's probably going to be the norm for the next few lectures. Most of us don't use the same lectures year after year, so we modify them all the time. That includes the accompanying lecture notes. If you have a laptop computer, I strongly recommend you just bring it to class. That way you can follow along with me if you want here, okay? Otherwise, you can get the notes a little bit later on. Now, today's lecture is going to be short. It's intentionally short so that we have plenty of time to go over the major lab project you're doing right now. I think I've only talked to directly maybe 1/4 of the students in this class. I want to remind you that your project is a 3-part project where each part builds on the previous one. I don't think anybody got the contacts right the first time around. All right, so if you choose not to submit that for reconsideration, that's fine. That's your own prerogative. But if you do not get the proper formation thicknesses, you're not going to be able to do part 3 of this project. So even if you have no intention of redoing things, you still have to see me to know where the right contacts are. I have to explain things to you, okay? That is incidentally intentional, all right? Now, today what we're going to be doing is talking about Isopach maps. How many of you have done Isopach maps before? All right, so you've done that in your employment. All right, so I didn't think this was something we actually did in our classes, which is kind of unfortunate. So we're going to be talking about these maps and how they work in the oil industry and how to do them, because this incidentally is part of what the last part of the project is going to be. Okay, so knowing how to do these things is going to be fundamentally important. Now, before we get started, I actually did something I haven't done for a long time last night. I took some time off. I rented a movie. And I got to tell you, I really enjoyed this movie, Scott Pilgrim versus the World. I've read the comic book. I'm a fan of the comic books and all. And I know the movie really bombed at the box office, so I was really dreading seeing it. But geez, that was a kick-ass good movie. So, Scott Pilgrim versus the World. Put your hand over the camera for a second, okay? I don't want this to go publicly also, because these lectures actually are, if you're in my mineralogy class, you've heard me, I was talking about this in class the other day, these things go online, and I don't actually have them hidden in any place so anybody can access them. And the geophysics lectures are actually far more popular than the other lectures I put on here. Apparently, when people are in classes in other parts of the world, they'll just go porosity logs, and it kicks on here, so I'm getting comments, which is kind of weird too, in broken English. All right, you can kill that now, and we'll... All right, so today, Isopach maps, top of formation maps. The more you can graphically illustrate what it is you are finding in the subsurface, the more you're going to be able to convince managers that you have the correct thing or correct area for drilling. This is yet another graphic way of illustrating how things look in the subsurface. Now, before we get to that, last time before we had the exam, by the way, you're going to get your exams back in Monday's class if you're wondering where they are. We talked about the third lecture. We had our third lecture on electric logs. We talked about the so-called porosity logs, which were the neutron logs, the density logs, and there's one log missing from that. What's the third log? Sonic logs, and I hope you remember that for the quiz or the test we had the other day too. Okay, we'll get to the sonic logs a little bit later on. I decided to throw this in now because of the lab assignment we have coming in tomorrow. A reminder, neutron logs are used primarily as a means by which to discriminate rock type as well as the amount of hydrogen that is within pore fluids or within the rocks themselves. And I gave you a list of criteria in terms of the types of rocks that have different responses based upon the hydrogen content. And there were some anomalous things here. For example, natural gas tends to have very low hydrogen content, whereas oil has much higher content. And that allows you to start making some determinations about where potential reservoirs are. And that's another thing you want to consider too. When you look at these logs, there's more information on these logs in the exercise than perhaps you realize right now. We also talked about the density logs, and density logs were a means by which to discriminate the nature of the elements that are within the rocks, and this is done on the basis of the interaction of electrons. The argument being that the more electrons you got, the
higher specific gravity the material is going to be. And again, that's a bit of a dangerous thing to do if you didn't know what the materials were. But of course, we're talking about a very limited possibility of materials in there. So it works for the most part anyway. And then we talked about the idea of using these in conjunction. And here's where you separate good geologists from the not so good geologists, is the recognition of where you start having multiple logs interacting with one another. So the crossover effect is an important means by which to look for things like gas content. And as I mentioned to you previously, unfortunately we don't get quite the same response when we're looking for oil, which is a much more valuable commodity right now. But hey, even if you can't find the oil, finding the gas is pretty important, especially if you get it associated with the top of a potential reservoir. If you've got gas on top, there's a good chance there'll be oil below it before you get to water. Remember, these fluids get stratified in the subsurface as well. All right, and sometimes these crossovers are not as thick as you see on this particular demonstration slide here. Sometimes they're very thin, but that is enough, if you're very observant, to be able to start concluding that there may be some fluid variations within a reservoir. And of course, you also have to be able to determine the porosity of the rocks. No sense just having this fluid if you know there's no porosity there. All of this stuff can be determined based upon these electric log responses. Now here's today's agenda, and it will be a relatively short agenda. The reason for this is that I want to have at least 15-20 minutes left at the end of the class today, so if anybody brought their logs in, I can give them some additional information about things, because I'm aware that some of you may not be able to meet me during my office hours. But again, I say this one more time, you need to get information about this. You need to find me one way or another so I can give you where the right contacts are. Otherwise, when it comes to doing the next phase of this stuff, you're going to be wrong. And folks, you don't get another chance to do the gamma ray logs. Okay, that's a one-up thing. So make sure you know where those contacts are. Now, before we get to that little break, we're going to talk about Isopach maps, very quickly go through them, and top of formation maps. I'm going to talk to you about what they are. I'm going to give you some examples of what they look like, and then I'm going to show you how to make them. And when I get to that part, make sure that you're making notes, because that is going to be pertinent to the lab assignment for tomorrow. And I'd rather not have to spend 20 minutes at the beginning of the class showing you how to do these things. I want you to be able to move right into this and start doing it basically now if you want to think about it, okay? All right, first of all, isopachs. Isopachs are basically contours. But what they are, contours that enclose areas of equal thickness. You're familiar with contour maps from your work in geomorphology. Contour maps show you surface topography. They show you elevations. Or if you wish, a contour shows you similar or identical elevations above sea level. Isopachs do the same thing, but this time in terms of thickness. Isopach maps can be done on surface exposures of rocks, and they can also be done in the subsurface, and that's where they're most particularly useful when you're dealing with petroleum or even in hydrogeology. Being able to determine the potential thickness of an aquifer or thickness of a reservoir, petroleum-wise, is very important, because that gives you the amount of pay interval, all right? It should reflect true thickness. Now here's where people often make mistakes. You've already seen how this works, because you've already had some experiences with logs that don't always give you the right amount of exposure. So suppose you've got an SP log that does this in one area, and you've got an SP log that does this in another area. If this formation is the same as this formation, you've got an absolute thickness. You can measure the top and the bottom, determine what the thickness is of that well. You can do it also down here. The problem is this. You've got the top of the formation, you do not have the base. If you start mucking around and saying, well, it's probably going to be about the same thing, that's where you get yourself in big trouble, because now you have estimated what the actual thickness is going to be, and when you put that data on your map, it's going to influence how the map actually turns out. And that's where people commonly make mistakes, because it will really change how your Isopach map looks. So this one is a no data point, this one is. That's important. We'll come back and talk about that when we get to showing you how to actually go about doing these maps. Otherwise, Isopach maps follow normal rules for all maps, which means scale bar, north arrow, legend, standard stuff in terms of orientation. It's a map after all, except it's showing you different information, okay? Top of formation maps, or base of formation maps, or whatever you want to call them, are not quite like Isopach maps. They're more like contour maps in a sense that what they do is they show you how far it is from the surface down to a particular formation. And here, these maps are normally corrected for surface topography. Now, we haven't done that for the logs we've done so far. In fact, I've been very clear on this. The whole idea is that if you're drilling in an area that's got hills, these things are usually determined in terms of depths based upon where the starting elevation is. But when you're doing a top of formation map, what you do is you take out the surface topography, more or less normalize it, and now the depths you're getting to the tops of the formations will reflect the true orientation or the true spatial differences across the subsurface. In this way, what you're looking at is original depositional topography. And this is something that is very important because it will allow you to not only determine the nature of the depositional environment, but also will give you some clues as to where there may be other types of potential deposits. Now, here's what I mean by this, okay? Assuming now that we have already taken out the surface topographic changes, if in the subsurface you're getting formations that more or less are doing this. Now you're going to look at this and you're going to say, well, this is obviously a thicker part, so this will show up in the Isopach map. But the question you need to ask yourself is, what the hell happened down here? Why was that there in the first place? It could be an unconformity. In fact, mapping out unconformities is a very important role in top of formation maps as well. Or it could have been some original topographic variation. For example, it could have been reflecting a channel. There could have been a river based right there. And if that's the case, if you do a top of formation map, then what you'll see is that you're going to get this type of transition where that might be the deepest part, and what it's giving you now is the orientation of the original channel. All right? That is really important because then now it allows you to start estimating where you might have potential other wells somewhere around the vicinity. Especially if the map area you're considering is here and the actual map that you've got data for is there, and you've got this type of trend, and a land sale comes up here, you could already get an idea as where the potential places are to drill if the trend of the river kind of is doing that. Now, of course, if it's a meandering river, as they often are, that's a little bit more challenging. But hey, that's what this is all about, okay? It's coming up with the best solutions for what you can't see at the surface. It's really cool stuff if you think about it. All right, what do they look like? Well, Isopach maps, as I said, can be stuff that's at the surface or at the subsurface. So let's start at some surface maps. This is an Isopach map showing you volcanic ash thickness associated with whatever this volcano is here. I can't even read it. I don't even know where that is. I just saw South China Sea, so it's going to be somewhere in Southeast Asia. I think it's Mount Pinatubo, actually, now that I think about it. All right, what you're looking at here are isopachs in meters. 30, 25, 20, 15, 10, 5, and I guess that's the 0 line. Where's it thickest? Duh. In the vicinity where the actual volcano is. Which way is the wind blowing? Or was the wind blowing when the volcanic eruption took place? All right. How do you know? That's where it's thickest. Okay, so you can obviously see why applying an Isopach or total ash thickness component to a map is useful, because it shows you more or less where ash was being distributed. In fact, we've done this type of thing for volcanic ash eruptions all around the world, and some of them actually show you just how impressive these eruptions can actually be. Here's a basic formation thickness. This is subsurface stuff you're looking at here now. This is the type of thing that you're probably going to pick up. Notice it's all done on the basis of township and ranges. These are all sections. No, actually, these are all these are all townships and ranges, so these are 6-mile blocks through here. And what you're looking at are local highs and local thins, or thinner areas. So in other words, this formation tends to come and go all over the place. That's essentially what you're going to be getting in your exercises when you do this, okay? And I think I'll probably put these things slightly out of order because I thought I had another volcanic ash bed here that was even more impressive. This is on the basis of centimeters. This one should have been the first one you see here. Another volcano, this time from Nicaragua, again showing that this is the distribution of the ash, and that's a town that was impacted by this. Okay? So very visually stimulating if you know what you're looking at. And of course you can modify it to make it easier to look at, as you would if you were in, say, a petroleum situation trying to illustrate overall thicknesses. What you can do is have a map that shows you thick areas and thinner areas illustrated by different colors. Now, I don't say that this is particularly the best and most effective color scheme to use. You can see what they've done is they've used different shades, where in this case the thickest stuff is the coolest colors. I tend to like going in colors that are fairly consistent. So if you're looking at Isopachs, choose a color. Choose red or blue. If you've got 5 blue shades of pencil, then use the 5 blues, where the thickest is going to be the darkest color. If you do not have 5 colors of blue, you can also imitate this by simply doing different amounts of shading. So the thinnest stuff is the lightest coloring, the thickest stuff is the thickest. I personally prefer colors you can see through. Reds and oranges and yellows are far better than blues, because I can't even read anything that's in here. Okay? But as I said, by coloring things, you can see from a distance where the thickest components are. And remember, when you're putting together something for display purposes, then you need to be able to make it clear as possible so people can see things from a distance. And here's another one. This is actually a relevant one, part of a PowerPoint slide that I stole from the US government, which is more or less, again, showing you isopachs in terms of thicknesses to a particular sandstone. And again, you can see how they've done in terms of, actually this is related to, that's something else, that's over here. The thicknesses are related to this scale here. So in this case, the darkest colors are the thinnest layers. So you have a chance to do isopach maps as part 3 of this exercise. Top of formation maps, again, I don't really have to spend much time on top of formation maps because that should be blatantly obvious. What you do is you find where the formation is, and you more or less make a map that shows you how far down it is to each of those. And again, these are pretty useful. Here you're looking at negative numbers. This is from the surface down. We're not going to do it that way. What we're going to do is actually measure it from the actual levels that are on the logs themselves. But here you'll see that this is 5,000 feet down. This is 2,500 feet down. So that's obviously a low based upon this mapping scheme. And this is actually associated with some sort of a major thrust fault, I believe, in this area. And this is, incidentally, from an actual oil-producing area in Wyoming. Okay? All right, now with that, we're going to turn the light. Number 1, you have a field map. And do not assume that I'm going to be able to give you the exact locations of all these things. It's irrelevant. You have one log that more or less goes in this direction like so. That would be the SP correlation. You've got another log that's going to go something like this, which is the gamma ray correlation. You also have some associated wells that are located in various places that are off the cross section. Each one of these wells can become an important source of data by which to fill in various isopach maps and various top of formation maps. All right, now consider you've got a well located right there. This well will have different kicks associated with the different formations, and again, don't worry about which one is which. The important thing is that you are able to identify which each formation is in your correlations. If you got your correlations right, that means you got your thicknesses right. How do you determine the thicknesses? Well, you physically measure it directly off of the logs. So if this happens to be, what was the first sense, the first limestone, Waikato limestone? If that happens to be the Waikato limestone, you can measure the top of it, the base of it. You've got the top of formation information, you've got the base of formation information, you've got the total thickness just by simply subtracting those two. You can do that for each of the formations you've got in each of the wells. Now, of course, it would help if you had some sort of a data table where you could actually just fill in the numbers for each of these things, okay? These are your source of data by which to do the maps. You've got the 5 wells that go this way. You've got 5 wells that go this way, one of which overlaps. So you've got 9 wells where you can determine the formation thicknesses of each of the formations. I will provide you with additional information for the remaining wells in the surrounding area. And I forget how many additional wells there are. I'll give you the numbers for that. Once you have those data, you're set. Because all you have to do now is to start adding numbers for each well for each of the assigned formations you have to do. So, one of those is probably going to be the Waikato limestone, sorry. Each one of the wells, you do not have to worry about putting the cross sections on here now. In fact, after a while, the cross sections start to get a little bit annoying in terms of redundancy, okay? But if this was the Waikato limestone map, for each of these points, you would record the thickness of the formation you got at that point. So if there was 100 feet here, and 125 feet there, and 85 feet there, and 75 feet there, and 80 feet there, and 95 feet there. You get the idea, putting numbers all along here. You will be responsible for producing the numbers for at least 9 of these sections. Sorry, 10 of these sections. 9 of the sections. And I will give you the numbers for the rest. Put all the number on there, and then it becomes essentially a contouring exercise. But instead of you contouring in terms of heights or elevations, now you're doing thicknesses. I forget what the actual number is I'm going to be asking you to do. It's probably it depends on the actual formation thickness. If you're dealing with a very thick formation, you tend to have a higher contour interval. If you're dealing with a thin formation, it's a thinner interval. All right? In the case of this, say I gave you a 10-foot contour interval. You would use standard contouring principles. Start at the highest point and work your way down. All right, so the highest point on this map with the data you have is 125 feet. 120-foot Isopach would be there. 110 there. 100 here. 90, and we're going to run out of data in a hurry, but you get the idea, would be there. 80, like so. They go off the edge of the map. Do not have it self-contained, and don't start playing silly 111 games where you take a contour line and do this because you think it's got to stay on the map. That's wrong, okay? You have all the mapping knowledge you need for this, and I'm expecting you to use proper mapping techniques. But I'm also expecting you to use Isopach techniques as well, where you would start to color in, according to whatever shade you wish, where the thickest parts were. And of course, because you're going to use proper mapping techniques, you would put a title on this, you'd put a north arrow on this, you'd put a scale on it. I'm going to give you the base maps, because basically it's just the maps you're going to be using. They're going to be on 8.5 by 11. We're not using big sheets or anything like that now, because we've got to save paper and all. All right? But it's up to you to do the contouring on this and to more or less get it in nice presentation mode. Some people, after they do this, cut out the maps and put it on a larger piece of paper, so you've got all the top of formation, all of the Isopach maps nicely displayed out there. Some people, incidentally, also use the same colors for the Isopachs that they used for their cross sections to give very nice linkages. And again, remember, if you're presenting this to somebody, you want somebody to be able to look and see exactly what it is you're showing, not have to ask you questions, or which one's that again, or anything like that, all right? What happens if you have a formation that pinches out? Because that occasionally does occur. If this is 50 feet, that's 40 feet, that's 30 feet, 20 feet, 10 feet, it is okay to have a 0-foot component to it. That's the pinch-out point. So if you happen to have a formation that thinned and is vanished on part of the map area, you give it a 0 thickness. That becomes your 0 line. And then everything on this side is left blank because it's not exposed in that area. And I'll tell you, looking at Isopach maps is a great way to look at the orientation of the pinch-out direction. Because remember, pinch-outs are commonly very good places to look for potential trapping mechanisms. So if you have a pinch-out that looks like this, you know that is, well, I guess we wouldn't actually drill between the 10-foot and 0-foot contour lines. There's not much pay zone there. But certainly considering something like this might actually not be a bad option if you know that this is also inclined in the up-dip direction. Now, folks, how would you determine where the up-dip direction was of an Isopach map from a thinned formation? What would you do? To look at the cross-section, but the cross-section just shows you along one line. Sorry? Thank you. Top of formation map. If you have a top of formation map that shows you that this also happens to be the highest part of the formation, then you're laughing. But if the highest part of the formation actually happens to be here or somewhere else, then you have to start taking into account those two variables. If it's raised up here in the middle, the pinch-out is irrelevant because it's down dip. All right? Information like this is vital for determining where you actually drill and where you actually start looking for petroleum reserves. All right? As far as the top of formation goes, top of formation is going to be a little bit tricky, okay? Because as I said, normally what we would end up doing, if this were a real exercise, I would give you top of the surface exposures, and you have to subtract all that and sort it all out. We're not going to do that this time around because frankly I haven't really thought that through enough to make it actually worthwhile. So all you have to do is just go to your electric logs, and if you happen to find the top of a formation at this point, use that as the top of formation interval. And then put that information on your map and then contour it around. Now here's where things are going to get really dodgy. Because when I put these things together, I wasn't really thinking too much about the end product as far as top of formation goes. So expect your maps to kind of go all over the place. In fact, I've never seen any two maps look exactly the same. I'll give you plenty of free rein in terms of this. Just do the best job you can, okay? All right, anybody have any questions? All right, well, that's what you're going to be in store for. And just to finish off right now, since I wanted to, as I said, give you plenty of time to talk to me about your exercises. Thursday, your SP corrected, if you chose to do so, and gamma ray log correlations are due at 2 p.m. I'm going to confirm that you handed them in and then give them back to you because you need them for part 3 of the exercise. Okay, so you'll get a series of blank maps as well as instructions again as to how to do the isopachs and all. I will specify which intervals I would like you to do. It's not going to be every single formation obviously because not every single formation was exposed everywhere, but they will be the interesting ones. So expect a series of about 5 to 8 maps, I believe. When we meet in Monday, your tests will be returned, and I will be going over fence post diagrams. How many of you've done fence post diagrams in stratigraphy, right? Good. I'm going to go over how they're useful in terms of petroleum and probably throw in a few other things in there as well. I'm working on getting that interview with that petroleum geologist sorted out as well, okay? So, tomorrow, be prepared for lots of fun activities. But you're almost done with that first exercise. Anybody have any questions? Yes?
What's the difference between an isolate and an isopach map?
I'm sorry, what's that?
What's the difference between an isolate and an isopach map?
Don't know. I think isolith shows identical rock types, doesn't it?
Okay.
Although why you'd want to do that, I don't know. I've never heard of anybody using that, at least not in this field.
I was just wondering, because I've always heard isolate maps.
Maybe actually a phonetic mispronunciation, I suppose. All right, if you've got your logs here and you want additional information, now's the time to hit me with it. I'm here for another 20 minutes. If you have not yet showed me your logs, for God's sakes, make sure you find out where the right correlations are. I'm giving the information away, but you have to come up and ask me about it. Thank you again, okay? Well, if you need notes, we'll get them from...